Well, hello once again, ladies and gentlemen. Mr. Dorfler back at you with another video in Intro to Chem Phys. This time we're continuing our discussion in Chapter 13, Section 3, and we're going to split Section 3 into two different videos, okay? Otherwise, it'll be kind of a lengthy video here, and I know you don't want something that's too time-consuming, if you will. All right, so we're going to split this into two, like I said, and we're going to concentrate today's video on the first half, and then the next video will be on the second half, okay? So far, this chapter, and you just got done being quizzed on, we discussed simple machines, we discussed work, energy, mechanical advantage. And so what we're working on today, no pun intended, is we are continuing our discussion over energy. This time we're looking at objects that are in motion or objects that are, let's say, raised above a certain point relative to another point. So let's again talk about energy. Energy sometimes is hard to put a solid definition on there because we use the idea of energy probably daily. You know, you say, I don't have any energy to get on my computer and watch videos. Okay, there's that type of energy that we say, or, that car has a lot of energy in it, enabling it to move or go from one point to another. Or there's, everything requires energy to operate in your household. All right, so each one of those scenarios is kind of different. All right, and so energy can mean a lot of different things. And so scientifically speaking, we had to put our thumb on it and say, this is how we define energy. Okay, energy is the capacity to do work or the ability to do work. Whenever work is done, energy is going to be transformed or is transferred from one system to another. Like, for instance, when lightning bolts strike the ground, a battery powering a flashlight, a moving bicycle. Okay, all of those have various types of energy that are going to be transformed or transferred to another system from an original system. Okay, let's take a look at what we can see in terms of what is going to be covered in this section. Potential energy, kinetic energy, and mechanical energy. As you see here, if you've ever seen a hydroelectric dam, it utilizes pretty much all three of these types of energies in order to function properly. You have potential energy. Typically, a hydroelectric dam is going to have a water that's going to be at some type of greater elevation in a sense, and that will fall down. And as it's falling down, that potential energy is going to be converted to kinetic, and then that water's falling. And so when that water falls, and then it gets into the generator wheel, it begins to spin that wheel. That's called mechanical energy. Mechanical energy, as that's spinning, is then also going to produce electrical energy. Okay, so we've got all these various types of energy. They're just being transformed and transferred from one system to another. So let's measure energy, okay? Types of energy that can be measured. An object or system at rest, okay? Unlike work in which object must be in motion to be measured, the transfer of energy from one object to a system to another can be measured. So it's measured by how much work is done on the receiving object. And again, energy is in terms of joules. Now, it's not the first time we've seen that unit, okay? This is because work or energy is the ability to do work. So we measure that in joules as well, much like what we saw with work. So we're going to be focusing on potential energy in today's video. And it's the energy that an object has simply because of its position, shape, or condition of the object. If you've ever seen, the old videos, you really don't see them anymore, but of when your building is being torn down, where you have a wrecking ball, okay, you have that big giant mass on the end of a cable, and it as it swings up here, that energy or that ball, as it gets higher above the ground, is actually increasing its potential energy. It's the amount of energy an object possesses based off of those three conditions. Okay. It's often called the energy of position because it is a result of the relative positions an object has within its system. Other examples, you might see a coiled spring or an archer's bow with the string pulled back. Okay, my wife just got done bow hunting over the last week. Okay, so you have to pull back on that bow in order for it to have potential energy. It's energy which it possesses. Other ones, we have elastic potential energy, defined as any object that is stretched or compressed to increase or decrease the distance between its parts of the system. If you think about a rubber band, when you have a rubber band just sitting in your hand, let's see if I can't find one here. And of course, there are none to be had. All right, I used to have a whole drawer full of them, and now they've gone bye-bye. Anyways, you hold a rubber band in your hand, it doesn't have really any potential energy. You don't have that until you stretch that rubber band when you get elastic potential energy. Okay, it increases the distance between its parts of the system. Okay, and so then you have basically energy stored in that stretched rubber band. Then you have gravitational potential energy. This is one we are mostly going to fix ourselves on, is gravitational potential energy. It's when we have a system of two or more objects separated by a vertical distance. That's when we're going to have potential energy. One of my favorite things to ride or to even use to describe potential as well as kinetic energy is roller coaster. Okay, when you go on a roller coaster, I guess I should say the majority of roller coasters, you take a chain lift, or you might even start off at the very top of a large hill. When you get to that top of that large hill, your position relative to the ground increases. And so now you have a distance between where you're at the top of the hill and the very bottom, where that bottom of the track is going to be once you go down the hill. That distance is going to help determine what is your overall potential energy. Now, as you begin to go over that hill and go down, that potential energy that you had will then be converted into kinetic energy. Okay, we don't ever get rid of energy; we just simply transform it or transfer it. So how do we calculate gravitational potential energy? Well, here is your formula to start off with. Again, you have this in your formula packet, so it's always good to have that packet with you. Gravitational potential energy, or as we call it, GPE or just PEG, depends which book you look at, is equal to the mass of the object times the free fall acceleration, which will always be gravity unless stated otherwise, and the height of the object relative to another point they are measuring to. So PE is equal to M times G times H. Again, H is the height. Mass must be in kilograms. Okay, there's that must again. The heavier the object, the greater the gravitational potential energy will be. Again, free fall acceleration is 9.8 meters per second squared, and the height of the falling object is going to be in relation towards where the object is falling and where we're measuring it, where it's going. Again, the higher the height the object is when measuring, or I should say the difference between the 2 points that you're measuring, the greater the gravitational potential energy will be. So if we have an apple, okay, we have two apples that weigh the same, have the same mass. One apple is located higher in a tree than the other. That apple that is located higher in the tree will have a larger amount of gravitational potential energy simply based off of the height. Another scenario we have is when we have two apples, again at the same height, but each apple has a different mass. The apple that has the larger mass, again, will have a greater amount of gravitational potential energy simply based off of its mass. So, in most cases, we will measure the height for gravitational potential energy from where the object is to the Earth's surface, so the ground, basically. Okay, that's the majority of the time. But we can also measure the gravitational potential energy between an object in motion and another stationary object, which is really more applicable to real life. Okay, if we have an example, this is a sad example, but I guess a bird's nest doesn't have to have eggs in it or babies. But when we have an apple in a tree as well as a nest, okay, the apple's height above the nest would be used to calculate the apple's potential energy with respect to the nest. So if you were to calculate a situation like that, you would take the distance between the apple and the nest, not the apple and the ground. You're going to get a significant difference in your calculations. So it's very important that you read the question carefully to understand between what objects we are measuring the height difference, okay? So again, here comes a slide that you should all have memorized by now. The steps to calculate, okay? And here we are calculating potential energy of an object. So again, PE, potential energy, it's in joules, okay? Mass is in kilograms, G is free fall acceleration, 9.8 meters per second squared, and H is in height, which is measured in meters. To determine the known, then determine the unknown values, insert those values into the formula, and make sure that you include the appropriate units after you've calculated everything mathematically. So let's look at an example here. We are to calculate the gravitational potential energy of the following. We have a 1,200 kilogram car on the top of a hill that is 42 meters high. All right. Let's get into our calculation mode here. I need to darken this up a little bit. So again, just a reminder, when we do this, if I can get, I'm having some troubles today getting my camera right. So again, PE is equal to M times G times H. And we are told that the mass is 1,200 kilograms. The height, if I go back to, wrong class. Height is 42 meters. And again, our G is our gravity, which is 9.8 meters per second squared. Before I put anything into the formula, I first ask myself, is our formula set up to solve for what we don't know? And are all the values that we do know, are they in the appropriate units? So yes, going back to the formula, we are to solve for potential energy. And our mass is in kilograms, our meters is in height. Our height is in meters, I'll get that right. And it's meters per second squared for gravity. So we can now go ahead and plug in our values here. Mass of 1,200 kilograms. I'm just going to make sure it's 1,200 and I didn't make a boo-boo. 1,200, okay. Multiplied by G, 9.8 meters per second squared, and then multiplied by our height of 42 meters. So I'm going to calculate all that. So 1,200 times 9.8 equals, and then take that, multiply it by 42, and you'll get an answer of 493,920 joules. But if you know anything about what's called significant figures, which we really haven't done yet, really it's just a method to present our information in the appropriate manner. And so since we haven't done it yet, this answer would be good enough. Okay, but if you do know what significant figures are, you would see that you would round this answer to about 4.9 times 10 to the 10 to the fifth, or if you had 49,000 joules. Okay, I know it's a lot. We haven't discussed significant figures yet. We will, though. We will. So that's the answer for the first one. Let's look at our second question here. A 65 kilogram climber on top of Mount Everest at 8,800 meters high. So again, PE equals M times G times H. Mass is 65 kilograms. H is 8,800 meters. And again, G is 9.8 meters per second squared. Units are in the correct unit for each variable. The formula is set up correctly. So take our mass of 65 kilograms, take our gravity of 9.8 meters per second squared, and multiply it by our height of 8,800 meters. And go ahead and plug that into your calculator. 65 times 9.8 equals times 8,800. We will get a big number, 5605600 joules. So 5,605,600 joules. So that's how you would solve for potential energy. Now, again, we can manipulate this formula to solve for any of those variables within that formula itself. Okay? So, again, we're only going to do potential energy today. Your next video will take a look at kinetic energy, so objects that are in motion. Okay? But until then, I will see you all later. Bye-bye now.